3. Okay, so this looks like a 3-part question. The Ksp of PbBr2 is 6.60 times 10 to the negative 6. And then basically it's asking what is the molar solubility in pure water? What is the molar solubility in 0.5 potassium bromide solution? And what is the molar solubility in a 0.5 lead nitrate solution? Okay, so I'm going to label this as question number 3. And I'll also give a brief, kind of like an introduction on like solubility. So let's say you have a solid with the following elements. So this is a subscript and an M, solid, really let's color code it so that you know that this isn't like an element. Basically, the coefficients that you have in front of the elements on the product side tend to be the same as the subscript on the reactant side, if that makes sense. So this is why I'm color coding it. So it kind of makes sense when you think about it. N and M are just numbers, and then capital M and X are just like different atoms. And then I'll also write the relationship between solubility product and also molar solubility. So it can be expressed using the following expression, where Ksp is equal to the concentration of your cation to the power of its coefficient. And then this is multiplied by the concentration of your anion. In our case is just X. So it should be N minus. To the power of its coefficient. Okay, so I'll also write out these different definitions. So Ksp is your solubility product And in this case, this is the molar solubility of the M ion. And similarly, this is molar solubility of X ion. Okay, so now we can actually get started with the question. So let's look at the solubility of the lead bromide. It starts off as a solid, and then we're going to break it down into its ions to show lead 2 plus aqueous plus a negatively charged bromine. And to balance out this equation, we're going to need to put a 2 in front of bromine so that we have 1 lead on both sides and then 2 bromines on both sides as well. And then to write out the Ksp expression, it's going to be Ksp is equal to the molar solubility of lead 2 plus times the molar solubility of the bromine ion root 2. And there's also going to be a 2 in there as well, but I'll show it later on. Basically, we're going to assume that the solubility of the lead ion is equal to S. And we'll also assume that S is also equal to the solubility of the bromine ion. So then for this question, since Ksp is 6.60 times 10 to the negative 6, that's going to be equal to S for the molar solubility of the lead times 2S squared. So that shows us our bromine ion. Okay, so now we just had to do a bit of math and try to isolate for S. So it's going to be equal to 4S cubed is equal to 6.60 times 10 to the negative 6. And this gives us a value of 1.18 times 10 to the negative 2. Molar in pure water. Okay, so we know our main Ksp expression for this reaction. I'm now going to do like parts B and C on the next page. This is 3 continued. So B asks, what is the molar solubility in the 0.5 molar KBr solution? So we're pretty much adding more bromine ions to this solid. So therefore, I can just write that the concentration of my bromine is now 0.5 molar. And then I can solve for my Ksp expression again. Let's just write it down. So I'm going to sub in the Ksp value as the 6.6 times 10 to the negative 6. Our unknown is the solubility of the lead, which I'll just denote as S, actually. And then I'm just gonna plug in the 0.5. And then we can solve for S is equal to 2.64 times 10 to the negative 5 molar in 0.5 mKbr. Okay, so we can do something similar for the last part of the question. They have 0.5 molar of this lead nitrate solution. So again, I can write my solubility of lead equal to 0.5 molar. I can then do the same thing I did up there and sub in 6.6 times 10 to the negative 6 for my Ksp value. And then I'm going to plug in the 0.5. And then this is going to be multiplied by 2s squared. And now we just solve for s. S squared is equal to 6.6 times 10 to the negative 6 divided by 4 times 0.5. And then S is calculated to be 1.82 times 10 to the negative 3. And this is in 0.5 m lead nitrate. Okay, so let's check out the answer from our junior tutor, starting with part A. Calculation of molar solubility. They have the same expression we have as well, and got 1.18 times 10 to the negative 2 in pure water. Part B, they have some ice tables involved, but ultimately they still get the same answer of 2.64 times 10 to the negative 5 molar. They do the same thing for question 3. You can also write it out as like an ice table. And they got the same thing, 1.82 times 10 to the negative 3. So this solution is correct.